we have a problem, kind of like how we started out at the beginning of the year. We said, what's the slope of a line, or the equation for a line, tangent to a function at a given point? Now we're asking a different type of problem. Here's the problem. How do we find solutions to polynomials that don't solve algebraically? And that's a really difficult question because, you know, there's a few ways that we can solve algebraically. One, your guys' favorite way. What's one way that you really like to solve polynomials? Factor. You love to factor, okay? You love to use the quadratic formula on your calculator. Some of you guys remember the rational roots theorem, which is a nice way to figure out good guesses for a polynomial and then work on solving from there. That's really good stuff. Newton found out a way, you know, how do we solve more difficult things? For example, let's say that you had y is equal to x to the fifth minus 3x to the fourth plus x squared minus 1. You know, what are the solutions to something like that? Well, yeah, exactly. Merlane's absolutely right. You give up. We cannot find ways to solve this algebraically. The fact is that you can solve quadratics by factoring a quadratic formula. Cubics, I've mentioned this before, there's a one-page formula that you can use. Quartics, there's a two-page formula you can use. They've actually proven that there's no nice way to solve quintics, and so, or any degree there above. And put yourself back in the day of Newton. You're going back to the time in this world where they are verifying shortly after, actually, that the sun was the center of our solar system. Okay? And so if you think of the type of precise calculation that they use to determine the rotation of the planets, the motion, time, all of some of the interesting aspects of physics and how our universe was constructed, wow, they had great accuracy, and they sometimes had to deal with some very difficult equations. So if you wanted to find a solution, let's suppose this, for example, let's just do a basic one. Let's say you wanted to know what the square root of 5 was to 4 decimal places. How on earth would you do it? Right now, you guys take out your calculator and you go to the square root of 5, right? Well, they didn't have that. So I guess you find it once, then make a table for it, right? But you don't exactly make tables for stuff that looks like this. So I'm going to show you a bare bones basic example of what Newton did, and I want you to appreciate it. It's absolutely genius of him, and he was a smart guy. So first thing is this. I'm going to write down a function, namely y equals x squared minus 5. X squared minus 5, where does that function cross the x-axis? Positive and negative square root of 5. Okay? If we were to solve for this equal to 0, we would get positive square root of 5 and negative square root of 5. I'm going to draw that graph, but I'm going to exaggerate the x-axis a little bit. 1, 2, 3, 4, 5. So this graph starts here at negative 5 on the y-axis, and it comes up and it crosses at the square root of 5. What two integers does the square root of 5 fall between? 2 and 3. Somewhere right about here. So I'm going to kind of draw my parabola like so. And Newton recognized that all irrational numbers end up being solutions to some type of polynomial. So if he wanted to estimate the square root of 5, he would first think about y equals x squared minus 5. Now, I'm going to do two things. This is the raw work where we produce the formula. And then over here, we are going to do the actual example. I apologize for the many laughs yesterday in the video. Kyle Ohms was really making a ruckus last year about gutters. He wanted to go in business to build them. Yeah. All right. So, what you need to do first, anytime you use Newton's method, is come up with a function. And in this case, we want to find what the square root of 5 is. And so our function that we use is f of x is equal to x squared minus 5. Y or f of x, it doesn't matter. So over here, I'm going to derive the formula over here. So you'll see the example, and we'll derive the formula. So our function we'll call f of x. Here's the beauty of what Newton did. Newton said, well, hey, I don't know what the square root of 5 is. I'm going to give a guess. Give a guess. Okay. Wow. Now, you guys are narrowing really close in on it. I'm going to pretend I wasn't that smart, and I'm going to guess 3. Okay? I'm off, right? I'm off, but it's okay. Yeah, yes. In this situation, Marlene actually asked a really good question. She says, could we guess 10? Yes, in this situation, it could be that far off. Some functions you can't be that far off. In this case, you can. We'll discuss that later. So I'm going to guess 3. Okay? Guess. For the raw work over here, we're going to call our initial guess x sub 0. All right? That's our initial guess. That's what we want to start with. Now, I got to jump a couple steps ahead so you understand the whole process, but here's what Newton said. Newton said, I can tell that 3 is a ways from that spot. Okay? But what I need to do is I need to get close to that spot. So what I'm going to do is this, is I'm going to figure out what the height of the function is at 3. Nope. Once I figure out the height of the function there, I'm going to write an equation for a line tangent using calculus. No, you guys, you're trust me, you don't see it. The formula ends up being like 2 steps. It's super easy. It's not going to take much work at all. Okay. Now, look, Newton says, hey, when I draw that line tangent, if I find its x-intercept, that x-intercept is extremely close to the solution. And then he would say, allow that x-intercept there to be my new guess. And he would do it again. And he would, find the height of the function, draw another line tangent, and look for the x-intercept. And you can see how quickly does he get to that x-intercept. It looks like it happens really, really fast. Yeah, it does actually. We'll do an example. You can really just do 2 or 3 guesses, and you come right on top of it generally very quickly. Curry has a question. Not necessarily. Most of the time, you can get to 4 decimal places within 4 guesses. It entirely depends on the behavior and the rate of the change of the function around the 0. So what I just drew up there, we're now going to walk through here. So his initial guess was 3. So after the initial guess, we say, well, let's find a point on the line and a slope and write an equation. So let's look at our example. If 3 was our guess, my point on my line will have an x value and a y value. What's my x value? 3. And how do you get the y value? Plug it in. And in this case, we get 4. Now, let's write an algebraic expression for that. let's see. So my point on my line has an x value, which was, what do we call it over here? X sub 0. And then what did we do with x sub 0 in order to get the, plugged it into the original function, f of x sub 0. Okay? Everybody follow me so far? Okay, now we need slope. All right. We want the slope of that line tangent. Andrew's correct. It is 6. How do I find the slope of the tangent line? Take the derivative and plug it in. Yeah, plug 3 in. So in order to find the slope, I would take f prime of x. What's the derivative of x squared minus 5? 2x. Plug 3 into there, and you get 6. Yep, so you plug 3, your guess in. Yep, your x value. So our slope is the derivative defined at our guess. F prime of x sub 0. Yes? Good. So, yeah, that takes the longest part right now for us, but we're going to come up with a really cool formula. I'm going to work it out over here, but the idea is then we need to, as you said, solve it. We want to find that x-intercept, right, Jalen? We want to find, so when you say solve it, we need to write an equation for a line and find that spot. Now, instead of actually writing a whole equation for a line, let's just find the x-intercept. That's actually going to be a little bit easier, okay? And so what I'm going to write now is we need an equation for a line. And we're going to use that equation for a line to determine the x-intercept. And I'm going to write my equation for a line this time as y minus y sub 1 equals m times x minus x sub 1. Now, let's think about this for a second. The x-intercept, when that occurs, what value do you know? Y is 0. When you cross the x-axis, the y value is 0. So I'm going to write this as x 0 is my x-intercept. Okay? All right. So I'm going to plug it in. Okay? We have y minus, I'm going to use my y1 value, being my point on a line, which is 4, equals, m is 6, x is x minus 3. Now, again, that was the one point on the line that we knew. Instead of writing the equation for the line in slope-intercept form, let's just find our x-intercept by setting y equal to 0. So you would have negative 4 equals 6 times x minus 3. Divide both sides by 6. Negative 2/3 is equal to x minus 3. Add 3. And you get 2.33 is equal to x. So 2.33 serves as my new guess. Where did the y go? The y is 0. We're solving for the x-intercept, so we set y equal to 0 and we solve there. Marlene, did you have a question? Okay, so question. Yeah. I'm not sure if I'm following exactly what you're asking, but we will write a form where it does end up being the function value divided by the slope. So see if this matches with what you're thinking. Okay, let's carry the same process through to write the formula for Newton's method, and all you guys will have to use is the equation on the test, which I give to you. So this is just showing you how we actually get it. So I have the equation for the line again, which is y minus y1 equals m times x minus x1. And you are looking for your x-intercept, which again we said occurs at x0. Okay, so remember with Newton's method, just going to go right back up there. Remember, we plugged in our initial guess, which was x sub 0, right on this green line. It gave us a height. We wrote an equation for line tangent, and now we're finding the x-intercept, which will be our new guess, so we could get really close to that next spot. So let's go about that process. Yep, when you have a new guess, you just do it over again. But the nice thing is you guys are going to see we come up with a really, really simple formula to use out of this. You just got to be patient, and let's just use this information, try to follow on and solve. Okay, so I have y minus, if this is my point on my line, and this is my slope, what represents my point on my line for my y value? F of x sub 0, good. Equals, what represents my slope? Good. The derivative of f evaluated at x sub 0 times, what is my x sub 1 value? We'll call it x sub 0, our initial guess. All right, I know that that looks messy, but it's really actually, it works out really nice. We can set y equal to what? 0, and then you have negative f of x sub 0 is equal to f prime of x sub 0 times x minus x sub 0. What am I trying to solve for? X. If you'd like to solve for x, what would you do to both sides? Divide by the derivative, exactly. Divide both sides by f prime of x sub 0. And you get negative f of x sub 0 divided by f prime of x sub 0 equals x minus x sub 0. What are we trying to solve for? So what do I do? Add x sub 0 to both sides. And if you do that, I'm just going to write the equation in reverse order here. You get an x equals, so we add that x sub 0 over, we get x sub 0 minus f of x sub 0 divided by f prime of x sub 0. And that is our new guess. And that is Newton's equation for his method. And all it requires is this. Well, I guess, yeah, so three things. It requires that you have a function, that you have a derivative, and that you have an initial guess. And that's it. It's a piece of cake. Let's try square root of 7. Yes. Yeah. We're going to estimate to 4 decimal places. All right, square root of 7, you guys have more room to write than I do with the marker, so estimate to 4 decimal places. Look at that. So we want to estimate square root of 7. And so we need 3 things. What would be your function that has a solution at the square root of 7? F of x equals x squared minus 7. Is anybody confused how I came up with that? Okay, so if you add 7 to both sides and square root both sides, right? Okay, so that's the first thing. What if I had, let's just ask this, what if I had the cube root of 11? What would be my, yeah. Okay, so you got to be able to come up with the function. You also need to come up with the derivative. What's the derivative? 2x. And you need an initial guess, x sub 0. What number would you like to guess? 2.63? For the next one, we're going to use Derek's guess. We're going to go right in as close as we can. For the nature of this, just to keep the numbers straight and simple for you guys, it's our first example. I'm just going to guess 3 again right away. I know it's between 2 and 3, right? So we'll use Derek's approach later. He's right. 2.6 would be a much better guess than 3, and you should do that. I'm just going to guess 3. Okay. So square root of 9 is 3. Square root of 4 is 2. You should. I'm doing it because I don't want you guys to get confused with the decimals. I want you to see how it works out with one integer first. Okay? All right. So x sub 0 is equal to 3. Newton's method says as follows. X, my new guess, is equal to x sub 0 minus f of x sub 0 divided by f prime of x sub 0. I have to evaluate that. What's x sub 0? What's f of x sub 0? 2. I just plugged the 3 into my original function. What is f prime of x sub 0? 6. So you get 3 minus 1/3, which is 2 2/3, or 2.667. I'm going to write it out to 4 decimal places because that's what I want to approximate. So 2.6667 would be the closest approximation. Take out your calculators. No. Yep. So let's try this. 2.667 and one more. And if we square it, not bad, right? Not bad. We can do better. And so in order to do better, what I'm going to do is I'm going to use that guess again. X equals, what's my new guess? 2.6667. And trust me, you guys, you know, as you're narrowing in on this, you got to use all 4 decimal places. Minus now I got to plug this. I got to plug f of x sub 0. 0.1113. But there's 3 ones. Okay, so 0.1113, good, divided by 5.333. So 2.6667 minus 0.1113 divided by 5.3333. We should again, we said we should have that that 4-3 there, and we press enter, and 2.6458. 2.6458. Okay, let's get to Curry's question, which was how many times do we have to do this before we narrow down to 4 decimal places? Has the 2 changed? No. Has the 6? Has that 6? Yes. So right now, we technically know we're only good to the first decimal place because the second one's already changed. Okay? So let's try it again. Well, fortunately, it's an easy formula and we all know how to use it, right? Okay. We want that one to be 4 decimal points. Yeah. Okay, so we try again. Okay. So now I'm going to use 2.6458. So x is equal to 2.6458 minus and we got to, can somebody plug that in for me to the original one? So we got to square this and minus 7 from it. Okay. Whatever. Divided by, and if we take 2 times this on the bottom, what'd you get there? And if you choose to include or exclude numbers here, it just may take you longer to actually come into the appropriate estimate. So okay. So let's try that. So we got 2.6458 minus parentheses 0.000257, you guys said, divided by 5.2916, and we get 2.6458, right? Oh, hey, look at that. We're done. Oh yeah, it was. And so for the next one, if you want, so we can do that for the next one if you want. But you guys see how quickly we came to this spot? Yes. Well, that would show you that you were correct to 4 decimal places. Okay? When you compare it to the last one. Now, let's do one more example together, but look at this problem again, you guys. Do you see what we did? This green dot here represents my initial guess, which was what? 3. I plugged it in, and then I got a second guess, which was this little black spot here, which was 2.6 repeating? That's what we had, right? 2.6667. So I ended up just having, and it ended up being just 3 guesses. And so you can see how quickly it narrows in there when you think about it graphically. Let's take Berkey's advice, and let's do the square root of 11. Or would you like to do the cube root of 11? Should we do a cube root? Just so you know how. Because you very well could have that example on your test. So let's do a cube root of 11. So if we want cube root of 11, first thing that we need is we need a function, which is what? X cubed minus 11. I need a derivative, which is 3x squared, and I need an initial guess. Did you already check your calculator? And I'm not using it. Bunch of dorks. Okay, I think that Ina's is reasonable. You know that 2 is too small. You know that 3 is too big. So let's choose 2.5. Okay. Thank you, Ina, for being the voice of reason. Two cubed would be 8. 3 cubed would be 27. You're trying to come up with 11. So we know it's between 2 and 3. Okay, 2.5. So we set up Newton's method, which says our guess is equal to our initial guess minus f of x sub 0 divided by f prime of x sub 0. So x is 2.5 minus 4.625. And it's okay, you guys, at this part, if you don't write 4 decimal places or you write more, it just may take you longer to actually narrow in on it. So that's kind of up to you, okay? F prime of that, so 3 times that squared, 7.5. So 2.5 minus parentheses 4.625 divided by 7.5, and we get what? 18.75. Okay. Everybody's allowed mistakes. 2.2533. Okay, 2.2533. So that, that narrowed it in, pretty quickly. We have this young man over here which commented that he wanted 2.2 as a guess right away. I guess we're pretty close. So now we have a new guess. X is 2.2533 minus, if I take 2.533 and plug it in, what do I get? $15.2321. So we get 2.2533 minus parentheses 0.4408 divided by 15.2321, 2.2244. Still pretty close, huh? Well, we gotta do it again. Yep. Okay, everybody pause. Pause. Watch up here. Watch. Okay, look. Look at the number on the top. 4.625. That's pretty big. Then you get 0.44, much smaller. Then you get 0.0062. You can tell when you're starting to narrow in because this ends up being your error. This is your error. And so we're going to come in pretty close here. Let's give this a shot. 2.2244 minus parentheses 0.0062 divided by 14.8439. Pulls it off. 2.2240, huh? The numerator really ends up being an estimation for your error. No. You would have to do it once more. We're just about out of time here, okay? But you would technically have to do it once more because you can see that the 4th digit is not the same yet, okay? But my guess is that your next try will be fine. And again, if you were to plug this in, and again, think of Newton not having a calculator and having to do all this by hand. This was a nice way for him to really come up with a good range. So here's what I want you to do, okay? Shh. Why don't you try, okay, for homework, try these 3 problems. On a separate sheet of paper, try these 3. Use Newton's method. Why don't you evaluate? Square root of 6. The cubed root of 4. And then one more. We'll go the square root of. Okay. That's it.